All right, so we are going to move into chapter 5 today. We are going to actually start the backbone to what this class is all about. So today in section 5.1 for this video, we're going to do areas and distances. So one of the big questions that we're trying to answer in Calculus 2 is something along these lines. We're trying to solve what we call the area problem. So as you can see on these two graphs below, it's not that easy to find the area of a region with curved sides. Now, it would be nice if it was a perfect geometric shape, but we're not going to always have these perfect geometric shapes. So what our goal is going to be is, can we develop an idea to maybe approximate the area under the curve and then kind of develop that into a more sophisticated or more technical way? So let's start with this example and kind of build the idea. I want you to estimate the area under the curve of the function 5 plus 2x squared from x equals -1 to x equals 2 using 3 separate rectangles of equal width. Now, when it comes to doing this idea of the rectangle method, we're going to use two methods, one called left endpoints and one called right endpoints. So the first thing that I notice here is that the interval you're trying to find the area on. We're trying to go from -1 to 2, which, as we can all hopefully tell, this has a width of 3 units. So if we want to divide this up into 3 separate rectangles, it makes sense that we could find that each width of each rectangle is 1, because you're taking a length of 3 and dividing it by 3. Now, if you recall back from geometry, the area of a rectangle is length times width. So if you're trying to find the area, let's say these 3 rectangles on the left. So we know they all have a width of 1. So when it comes to finding the area here, I know that all 3 pieces, we're going to end up doing 1 times the height of each rectangle. So what I'm going to do really quick is kind of write my 3 areas separately. So, but you see they all have a common width of 1. In each of these other parentheses, I'm going to find the height of each rectangle. Now, since this is called the left endpoint rule, what we are technically going to do here is we're going to start on the far left, which is at -1, and you're going to measure the height of how far it takes to go up to touch the function. That will dictate the height of this rectangle. Now, my line's a little shaky there, but as you can tell on the little dotted lines over here on the y-axis, each of those tick marks is a half unit of length. So let's see, that would be 6, 6.5, 7. So the first rectangle has a height of 7. All right, so you move over to the second rectangle, which once again, you're going to start this time at 0. You're going to go up to the height of the rectangle. And if you measure that height, you can find that it is equal to 5. And you continue that trend for the number of rectangles that you need, always using the left-hand side of the interval. So on the -1 to 0 interval, we use -1. On the 0 to 1 interval, we use 0. And then on the 1 to 2 interval, we use 1. And if I measure the height up here, we actually get lucky a little bit. It's the same height as the first rectangle, which is 7. Then it's just a simple arithmetic problem. This would come out to be 7 plus 5 plus 7, which comes out to be 19 units. So what I am claiming here is that the approximate area under this curve is about 19 units. Obviously, that is not correct because, as you can see, I'm missing this piece and this piece. And this extra piece I have here is not enough to make up for that lost area. So this is actually what we call probably an underestimate. So a thing that we can do here to maybe find a better approximation is, why don't we use the other side of each interval? So if you look over here at the right endpoint example, I'm going to use the exact same interval from -1 to 2. That is still 3 units wide. The only difference this time, like I said, the widths are not going to change. They're all going to be a width of 1. But to find the height of each of these rectangles on each interval, I'm going to use the right-hand side of the interval, which means, for example, and usually I start from the right when I'm doing right endpoints. From -1 to 2, I'm actually going to use the 2 this time instead, because that's the right-hand side of my interval. And if I measure the height here, let's see, 12, 12 and a half, that's going to be 13 here. So once again, when you're finding the area, while they all have widths of 1, you're trying to find the height of each of these rectangles, and we're going to add them together. So the first height has a height of 13. On the interval from 0 to 1, I'm going to use the 1 as my right endpoint, which we actually did a minute ago, and we found that to be a height of 7. And then on the interval from -1 to 0, we're going to use the 0 right endpoint to measure our height to be 5. Then when you calculate each of these areas of the 3 separate rectangles, this would be 13 plus 7 plus 5, which comes out to be 25 as our area. Now, as you can tell this time, the only piece we're missing under the curve is this little white area right here. But these two bigger areas obviously overdo that. So this would actually be called an overestimate. Now, the idea we're about to develop here is how can we get a better approximation? Well, we did left endpoints and got something way too small. Right endpoints gave us something way too big. Is there a way that we can find it to be better? And there is, and that's going to be on the next slide. One thing I am going to note here is what's going to save us some time on the next few problems is that what you will notice about all of these rectangular area problems is that they will always have the same width. So if you look at the left endpoint, for example, another way that we could write this is that since they all have the same width of 1, since that could be called our greatest common factor, if I were to factor that 1 out of all 3 of those additions, essentially you could just add all of the heights together and then multiply it by the common width. While that's not a big deal right here because the widths are 1, this will save us a lot of time when our widths are not 1 and they're fractions, as we're going to see on the next slide. But this is the idea of approximating area under a curve using a rectangle. So the first thing we're going to do next that maybe improves our estimation is to increase the number of rectangles. If we were to shrink the size or the width of each rectangle, we probably could get a little bit better approximation. So as you can see, this is the exact same function. So this is still going to be f of x equals 5 plus 2x squared. The difference this time, though, is I want you to use 6 rectangles. So as you can see on this graph on the left, we're still going to go from -1 to 2, which is a length of 3. But since I have to divide this up into 6 rectangles, if you were to take the length of 3 and divide it by 6, you're going to get half unit increments. So each one of these widths here, I'm going to write them all up for the first time through this, all of these rectangles are going to have a width of 1/2. So using the idea I showed you a minute ago, when you calculate the area, and we're going to do the left endpoint in red again, since all 6 of these rectangles are going to have a width of 1/2, to save myself a little bit of effort, I'm actually going to factor out the 1/2 here. And then I'm just going to measure all of the heights of these 6 rectangles, and then I'm going to calculate and add them together. Since we're doing left endpoints here, on the interval from -1 to -0.5, you're going to always use the left-hand side of each of those intervals. So the first rectangle, I would use -1, which we actually did this one in the last one, so you should have the same height. We get a height of 7. Add to that the next height. The interval from -0.5 to 0, if I were to use -0.5 as my height, that would put me up to, let's see, that is higher than 5. It's going to be 5.5 there. So 5.5 is the height. All right, and continue this. The interval from 0 to 0.5, I'm going to use 0, which has a height of 5. All right. The interval from 0.5 to 1, I'm going to use 0.5, which has the same height as the second rectangle, which is 5.5. All right, and then 1 to 1.5, I'm going to use the 1, which puts me up at 7. I'm going to kind of run into the graph on the right, but that's okay. Remember, I'm doing the left endpoints in red. And then finally, the sixth interval from 1.5 to 2, if I were to measure up to 1.5, that would put me at, let's see, 8.5, 9. That's going to be at 9.5. And once again, these are the 6 heights of all these rectangles. And we're going to multiply all of the heights by the common 1/2. Now, like I told you, it's going to be a lot easier here if you just add all of these decimals together. So if we do a little mental math here, let's see. If I add all the whole numbers together, 7 and 7 and 5 is going to be 19. 5.5 and 5.5 is 11. Plus 9.5 is going to be 20.5. All right. So that's going to end up being 1/2 times 39.5. All right. And then multiply and then dividing that by 2. Like I said, you can give me the decimal if you want, or you could just leave it as 39.5 over 2. This would be the hot area under the curve using left endpoints here. All right, very good. Now, doing the exact same idea, so I'm going to go a little quicker through this one. Do right endpoints. So you're doing the exact same interval. -1 to 2 is a width of 3. You're going to divide this up into 6 rectangles, but this time you're going to use the right-hand side of each interval. So if you go from right to left here, the interval from 1.5 to 2, you're going to use that 2. So let me start the area problem off here. You still have the common width of 1/2 all the way across. So if I use 2 as my first height, that's going to be all the way up there at 13. All right. From 1 to 1.5, if I use the 1.5, that's going to give me a height of 9.5. Oops, sorry, not comma, plus 9.5. Plus from 0.5 to 1, use the right endpoint for 1, which gives me 7. All right. From 0 to 0.5, we're going to use 0.5, which will get me up to 5.5. All right. -0.5 to 0, we're going to use the 0 as our height, which is +5. And finally, from -1 to -0.5, we use the right endpoint again, which will get me to 5.5. You'll know you're done because you'll have the number of rectangles as numbers being added. I have 6 heights for the 6 rectangles. Now, once again, doing a little bit of arithmetic here. If I were to add all these numbers together, starting with the whole numbers, 13 and 7 and 5 is 25. And let's see, we once again have the same 3 decimals as the last one, so we're going to add 20.5 to this, which will give me half of 45.5. And if you want to calculate the decimal there, you can. But if you would also, you could just leave it as 45.5 over 2. But remember, you won't have a calculator on your test, so I'm happy if you stop right there. But that is the first technique we could use to maybe increase our estimation. The more rectangles you do, the better. The problem you're probably starting to notice is that this can get very tedious the more and more rectangles you get. Now, before we do the second technique of estimation increasing, one thing to note here is that so far, every single height of these rectangles has fallen perfectly on a tick mark. That's not going to always happen. So on the next example, one of them is going to not fall perfectly, and we're going to have to do a little bit more work than we've done so far. But I'll talk a little bit more about that when we get there. But there's a good example of increasing the number of rectangles. Really, the last thing that may improve your estimation is that instead of using the left endpoints or the right endpoints, it might actually be better to use what we call the midpoint rule, which means that each of the intervals that we've talked about so far, instead of using, let's say, the left or the right, go right smack dab in the middle and use that one instead. So let me kind of show you using the 3 and 6 rectangle idea again. Now, once again, I have not changed the function here. Both of these are still f of x equals 5 plus 2x squared. And that's going to play a role in a minute, so make sure you note that down. All right, so over here on the left, since once again, all of these intervals have not changed, we're still doing a length of 3 is the width. If I want to use 3 rectangles, that means each of my widths are going to be 1, because the interval of 3 divided by 3 rectangles is 3. So when I calculate the area here, you can factor out the common width, which in this case is 1. The difference this time is that if I go right in the middle of each interval, so this would be at negative 0.5, and I were to measure that height up, this one's actually not bad because it falls on one of our tick marks, which is actually at 5.5. Then if I go to the second interval from 0 to 1, if I go right in the middle of that interval at 0.5 and measure my height up, it's actually the exact same height as the first rectangle. So we get another height of 5.5. And then finally, on my third interval from 1 to 2, if I go right in the middle at 1.5 and measure straight up, once again, try to draw the best straight line I can. It's kind of hard on my device. But this one actually also falls on a tick mark, and I believe that comes out to be 9.5. Add all of those decimals up, which once again, that's the same 3 decimals we added a minute ago. That would be 1 times 20.5, which multiplying by the common width of 1 doesn't change anything. This is going to be 20.5. All right, so on that example, midpoint wasn't that bad. Here's where midpoint can get a lot of people in trouble because it's a great estimation, but it can be very difficult if you're not careful. So this time, when we calculate the area, we're going to be very, very careful here. Once again, a width of 3 from negative 1 to 2 divided up over 6 rectangles is going to make the width of each rectangle 1/2. Here's going to be your problem. When you go to the midpoint of each interval, so let's say from negative 1 to negative 0.5, this is negative 0.75. So if I were to go straight up to my function, the problem is that it does not hit perfectly at 6. It's a little bit higher than 6, but you can't just say 6 point whatever you want. Unfortunately, what you're going to have to do a lot here is you have to go up here to the top, a lot of scratch work. I'm going to take the original function and I'm going to replace the x in it with the number you're trying to evaluate. In this case, negative 0.75 is the same thing as negative 3/4. If it doesn't fall perfectly on one of your tick marks, you're going to have to plug the value you're measuring into the original function to find the height. So I converted negative 0.75 into negative 3/4, and we're going to plug it in. So in this case, that would be 5 plus 2 times. That would be 9 over 16. And that would be 5 plus 9 over 8. And then combining those, once again, I'm going to switch, that should be an equal sign in the middle, not a plus. I apologize for that. And my words are small. Okay. So that should be an equal. I apologize for that. So that would be 49 over 8. And that's the height of the first one. So once again, this is probably the worst one of the 6 we're doing. Your second interval from negative 0.5 to 0. This is technically negative 0.25, which if you go straight up to your function, that is not on a tick mark. It's between the 5 and the 5.5 tick mark. So you're going to have to actually calculate this. So what I'm going to do is I'm going to take the original function, and negative 0.25 is the same thing as negative 1/4. So that's squared. That's going to be 5 plus 2 times 1 over 16, which is equal to 5 plus 1/8. And if you were to put those together, you would get 41 over 8. Now, while that is a lot more tedious than what we've been doing so far with decimals, here's where it pays off. If you look at the midpoint of the third interval between 0 and 0.5, while that is positive 0.25, you notice that the height is the exact same as the second rectangle. So don't calculate it again. We already found that to be 41 over 8. And also for the fourth rectangle between 0.5 and 1, which is 0.75, if you go up to the height of that rectangle, it's the exact same as the first rectangle, which we found to be 49 over 8. So that saves a little time. You have to do it's the third and fourth. But the fifth and the sixth are different numbers. So on the fifth rectangle between 1 and 1.5, that would be 1.25, and I'll actually draw the line this time. You can tell that that is a different height, and it's a little bit higher than 8 if you were to go across. So if I were to plug that in, let's see, 1.25 is the same thing as 5/4 if I plug that into the function, which is 5 plus 2 times 25 over 16, which is 5 plus 25 over 8. And if you were to put those together, that would be 65 over 8. See, it can get a little tedious. Almost done though. The last one, 1.5 to 2. This is going to be 1.75 officially, but as you can see way up there at the top, that is not going to fall on a perfect number. It looks like it falls a little bit higher than 11, but let's figure out exactly what it is. So 5 plus 2 times, let's see, 1.75 would be 7/4 squared, which is 5 plus 2 times 49 over 16, which is equal to 5 plus 49 over 8. When we add those together, this is going to give us 89 over 8 when you put them together. All right, you got the hard part out of the way. You calculated all those heights. Like I said, that's the worst it will ever get. Now you've got to put all of these together. So let's see, do a little mental math here. Since they all have common 8s, I know they're going to all combine into an 8 on the bottom. Oh, let's see. If I were to put all of those together, a little mental math here. That should be 334 over 8. And then I can simplify this because I know that 2 will go into 334, and this will give us 167 over 8. And that would be your answer as a fraction. Now, I'm sure someone's thinking, when we did all these conversions up here, could we have done that as decimals? You can. There's nothing wrong with decimals. But usually when the arithmetic gets a little bit harder, I usually go with fractions because it's easier for me to work it out on the screen for y'all. If the tick marks work out perfectly like the first 5 did, then I usually just use decimals. But whichever way is more comfortable with you. You could have used fractions on all of these on the first 5 if you wanted to as well. But as we've seen on the first few slides, we're trying to estimate the area under a curve. So we've done the rectangle method with 3 and 6 rectangles respectively. We've done left endpoint, right endpoint, and midpoint. And so far we've figured out that the more rectangles, the better, but it's a lot more work if you do that. And then also midpoint's probably a little bit better than left and right endpoint, even though it's a little bit harder. All right, so now that we've kind of seen how tedious that can be, let's start developing an idea to maybe make this a little bit better. That way we can increase the number of rectangles, but maybe not have to go through all of the tedious process. So as we just talked about, each rectangle has an area that is found by multiplying the base times the height. Let's start labeling some stuff. Let's call the base delta x, which we found earlier, delta x is going to always be the same thing for every rectangle. And while I didn't formally actually work this out by hand, how we calculated delta x every time is we took the width of the interval and we divided it by the number of rectangles that we wanted to use. Or if you want a more formal definition, if you're given an interval from A to B, delta x can be found by doing B minus A over n, where n is the number of rectangles. And as we kind of just visually showed you from going from 3 to 6, the more rectangles we divide the region into, the more accurate our area approximation will become. So if you remember back in Cal 1, when you did limits early on in that class, that's what we're about to get back into. So limits don't go away just because you finished Cal 1. I want to let the number of rectangles approach infinity. Now we can't formally let it be infinity because dividing by infinity would make it 0. But if we let n approach infinite number, then we can actually calculate this. So what does this allow us to do? This leads us to the first big definition of this chapter. The area A of the region S that lies under the graph of a continuous function f is the limit of the sum of the areas of the approximating rectangles. So essentially, you want to find the area of infinitely many number of rectangles. Now that's not plausible by the way we just did it earlier, but we're going to get into how we can do this by hand going forward. But here's the more formal definition. And I just wrote this for right endpoints. So when you see these R's and L's, these are just left. That just represents left and right. If it was M, it would be midpoint. But most of the things in this book are defined as right endpoints, but it all represents the same thing. All right. So, oops, sorry about that. All right. So what we can do is we can take the limit as n approaches infinity of all of the right endpoint values, which is going to make us look something like this. It would be the limit as n approaches infinity. And as I just showed y'all on the midpoint rule, you're going to have to actually calculate all of these function values as you work from right to left. Now, as you can see with the dot, 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 since there's infinitely many of these, that's not plausible to do. That's okay. But we'll get into how we fix that in a minute. But we're trying to define it formally right now. Now, one thing that I usually do different from the book is that since all of these have a delta x in common, these delta x's can actually be factored out in this case. So you can actually do the limit as n approaches infinity of delta x times all of the function values added together. That's what I was doing with the 3 and 6 rectangles. Not everybody likes to do that, but I just figure it's a little bit easier to work out, because if we can isolate this delta x term, it'll just make things a little bit easier going forward. The same thing can be defined for left endpoints and midpoints, but it's all the same formula. All right, so here is the formal definition. If you want to find the area under a curve, let me go back one slide real quick. Writing out these infinitely many f of x functions is just not plausible. It's impossible to do because there's infinitely many. So what we're going to introduce today is what we call a sigma notation. This is a more compact way to write out what we call these infinite areas. So we can actually define the area under a curve in the following way. We're going to keep the limit part. It is the limit as n approaches infinity. You can see that you have a summation here, and we are going to do a summation. The number on the bottom is where you start. So you're going to start at I equals 1, because you need at least one rectangle to make this work. And you're going to go all the way up to an n number of rectangles. Now, in the end, we're going to let n go to infinity, but we can't do that until we actually work out the summation. All right, inside the sigma, you have the common delta x, which remember you can find by doing b minus a over n. That's common. And here's the one other new thing. Instead of doing infinitely many f of x functions, we can write it as one f of x function, but we're going to call it f of x sub I. X sub I is not just going to be a common x. You have to then substitute an x sub I variable in, which would be your a value, which is the beginning of your interval, plus an I, which is the I value here, multiplied by the delta x that you're trying to do. All right. Now, setting these up is going to be the first challenge we have to do. In this section, it's all about setting up. In the next video, when we do section 5.2, we'll actually talk about how to work these out by hand. That's in the next video. All right. So, example 4, use definition 2 to find an expression for the area under the graph of f of x as a limit. Do not evaluate the limit. Like I said, I'm not going to make y'all evaluate any limits today. We're going to always just set them up. Next video, we'll work them out. So the function that I picked is f of x equals x squared times e to the x on the interval 0 to 4. Now, the big thing that you'll hear me harp a lot in these next two videos is that you can't do this area formula until you find these two purple boxes here. So you're going to have to first calculate delta x, where our a value is 0 and our b value is 4. So if we were to calculate our delta x, this would be 4 minus 0 over n. And that simplifies into 4 over n. Remember, the n is going to eventually go to infinity in the next section. For now, we'll just leave it as n. All right. X of I, which can be found by doing a plus I delta x, where a is going to be 0 plus an unknown I value multiplied by delta x, which is 4 over n. When you simplify all of that out, you will end up getting an x sub I value as 4i over n. And then using those two found values, we are now going to plug them into this area formula. So the area under the curve of this function on this interval can be found by being the limit as n goes to infinity of the summation from I equals 1 to n. So when it says f of x sub I, that means you need to go to the function that I gave you, and both of those x's need to be replaced with the x sub I you just found. So this would be 4i over n all squared times e raised to the 4i over n. This is f of x sub I. Then you have to multiply all of that by delta x, which we found to be 4 over n. And that is your setup for the area under the curve. Now, like I said, in this section, in this video, we are not going to calculate this out. But this is something that we will see how to do in the next section, because we got to learn how to deal with these i's, and that's the problem in evaluating this. So, but very good. That is how you set up the exact area under the curve. This is not an approximation. When we calculate this out, this will be the exact answer that we need. Let me just do one more so that you have it in your notes. As you can see, I don't have the formula up here this time, so I will write it before we get started. So I want you to use the same definition to write the expression of the area under the curve for f of x equals x plus the natural log of x on the interval 3 to 8. Right, so remember, to find area, this will be equal to the limit as n goes to infinity of the summation from I equals 1 to n of f of x sub I times delta x, where delta x is equal to b minus a over n, and x sub I is equal to a plus I delta x. Once again, you cannot find the area formula until you calculate these two unknowns down here at the bottom. So the first thing I'm going to find is delta x. I'm going to take my b value, which is 8, subtract my a value, which is 3, divide it by n, and that simplifies into 5 over n. X sub I, I'm going to take my a value, which is 3, and I'm going to add to that I times my delta x term, which is 5 over n, and putting those last two terms together gives me 3 plus 5i over n. Now that I have both of those unknowns, we can plug them into my area formula. So the area under the curve is going to end up equaling the limit as n goes to infinity of the summation from I equals 1 to n. So f of x sub I, both of those x's in the original function need to be turned into x sub i's. So this would be 3 plus 5i over n plus the natural log of 3 plus 5i over n Now, all of this, I'm going to put it in big brackets, all of that now needs to be multiplied by delta x, which is 5 over n. And that is the formal definition of the area under this curve. Like I said, in this section, all we're doing is setting up. In the next section, we will talk about how to evaluate things like that. All right, and then just to make you think a little bit before we go into the last thing for this section, what if you have to go backwards? What if I actually give you the limit definition of the area under the curve, and I want you to rewrite this by telling me what's the function, all right, and then what's the original interval? So do you know what you're actually working with here? All right, so in this case, I gave you the limit as n goes to infinity of the summation from I equals 1 to n of 1 over 1 plus 2I over n, all multiplied by 2 over n. So keep in mind on your definition, if you match this up, so let me write this over here real quick. The area formula is the limit as n goes to infinity of the summation from I equals 1 to n of f of x sub I times delta x. So that means all of this is f of x sub I, and this part is your delta x. From this, you have to calculate your a value, your b value for the interval, and what the original function is. Honestly, when you're doing this, I think the easiest thing to find first is your function, because all you have to do is take the f of x sub I, and whatever the term is that has the ugly I term, that's really just an x that you're substituting in. So I know that my original function is just 1 over 1 plus x. All right. And this, now you got to find your a and your b value. So a is going to equal something, and b is going to equal something. Now remember, you have two formulas that you remember. Delta x is b minus a over n, and x sub I is a plus I delta x. The first thing that I notice is that inside of my parentheses here, there's not a number being added to the I over n, which means that if my x sub I is equal to just 2I over n, then my a value is understood to be 0 because there's not anything being added to it. So I know that my a value is 0. And since my delta x term is 2 over n, which means the 2 is coming from subtracting the b and the a value from each other. Well, if I know that a is 0, what minus 0 would give you 2? Well, that would be 2 in this case. So that means that the original interval that you're testing on is the interval from 0 to 2. That's a little bit more of a critical thinking because you're not really doing any work here. It's all about taking the formula for the area under the curve and kind of dissecting it and finding the bits and pieces that set it up. So just wanted to make sure you saw that because we'll see some more stuff like that going forward. All right. The last thing I have planned for this section, for this video, is to do a more application of what the area under the curve is doing. This is called the distance problem. So this is one of many different distance problems that we'll see in this class. So this one's a pretty straightforward one, but let's talk through it together. So examples 7, 8, and 9 are going to all look very similar. I'm just going to give you some different information so we can dissect it. So example number 7 says, the speed of a runner increased steadily during the first 3 seconds of a race. Her speed at half-second intervals is given by the table. Find the lower and upper estimates for the distance that she traveled during the first 3 seconds. Use n equals 6. All right, so what we're going to do here is that, if you remember a formula that I just gave you, delta x equals b minus a over n. This is the only formula we have to use because we can't use x sub I because I don't have a function. I just have a bunch of numbers, but we can still use delta x. Well, my b value here is going to be 3, and my a value is going to be 0. And they want us to divide this up into 6 different rectangles. So I'm going to divide it by 6. And that does simplify into 1/2. All right. Remember earlier when we did those rectangle problems is that since the delta x will be in common with every single area, you can actually factor that out front. So when it says find the lower and upper estimates, let's start with the lower estimate. Since this runner is increasing speed, that means that the lower estimate will actually come from the left endpoint, because the further to the left, the numbers are smaller. Now I'm going to factor that 1/2 out front. So in red here, if I were to calculate the first 6 time measurements, you're going to do 6, and you have to go in half-second intervals. That would be 0, 6.2, 10.8, 14.9, 18.1, and 19.4. After that, you stop. You don't use the 20.2 because that's technically on the right-hand side of that last interval. You count the first 6 numbers, and these are kind of like your heights of your rectangles. You would go through and add all of those together. Let me roll all this down for you. And then you would calculate that. Now, to save a little bit of time here, I'm going to go ahead and give you this answer just because the video is getting kind of long here. I know some of you are getting kind of antsy. But add all those together, divide it by 2. Like I said, you can leave it as a fraction, or if you actually calculate it out, I got the answer to be 34.7 feet when I calculated it earlier. Now, the big difference on your homework is that make sure you get the lower and the upper estimates correct. So remember, the lower estimate starts from the left because her speed is increasing. The upper, while you're going to use the same delta x, which is 1/2, you have to start on the right-hand side because to get her upper estimate, you don't want to have to use that 0. So if I start on the right-hand side, this would be 1, 2, 3, 4, 5, 6. You would add the 20.2 all the way down to the 6.2, but you don't include the 0 because that is part of your left endpoint of the first interval, not the right endpoint. So if I were to add all of those numbers together, essentially you're just replacing the 0 with a 20.2. Now that's the big thing here, but I'm actually going to write it all the way out. And once again, just to save a little bit of time here, if you were to add all these decimals up and divide it by 2, you can leave it as a fraction, or I calculated it out to be 44.8 feet. And that's just kind of showing you where rectangles can be helpful, so we can approximate how far certain people run if we know their measurements in certain intervals. Obviously, more intervals the better, but as far as doing it by hand, this is not too bad to do 6 intervals. Now, that's a pretty good estimate, but remember, you don't have to measure in half-second intervals. You can literally measure in any intervals they give you. So to save a little bit of time here, use the exact same data. What if I change one small thing? What if we only want to do it in n equals 3? So what if I only want to do 3 rectangles this time? Now, while none of the numbers change, what is going to change first is your delta x, because the width of each rectangle is not going to be the same this time. While the b minus a is still the same, 3 seconds minus 0 seconds, if you were to divide this by only 3 rectangles, you get a delta x value of 1. And when I go to calculate the lower estimate, so there's 2 big things to note here. Number 1, you can still factor the common delta x out, which is going to end up being 1. But remember, you only need 3 numbers here because you're only doing 3 rectangles. That doesn't mean do the first 3 numbers. Since these are 1 second intervals, while yes, 0 will be your first measurement, don't use the 6.2. You have to use the 10.8 and the 18.1 because each of those are 1 second apart. Because technically you don't know the 6.2 because you were only measuring this at every 1 second interval. So when I add all 3 of those numbers up and multiply them by 1, this is a little bit easier to do, you should get 28.9 feet. That is our lower estimate for how far this runner traveled. And likewise, when you do your upper estimate here, your delta x is still going to be 1, so you can factor that out to the front. And then if you start on your right endpoint, so we're going to start all the way out here at the 20.2, and then you do 1 second intervals going backwards. You would do 18.1 and 10.8. So just like the 6 intervals, you're really just replacing that 0 with a 20.2. So I would do 10.8 plus 18.1 plus 20.2, which comes out to be 49.1 feet. The big thing there to note, though, is that the number of rectangles, whatever your delta x comes out to be, that is the measurement that you have to increase. So you went up by 1 second increments versus the previous problem, we went up by half-second increments. So please make sure you read the instructions when you're doing your homework. And I have one last problem to do, and this video will be done. The other issue that we have students run into is that they don't actually pay attention, and they just assume that the left endpoint is always the lower and the right endpoint is always the upper. So I found a problem in your book that goes against that. All right. So let's do this one to wrap up this video. Oil leaked from a tank at a rate of R of T liters per hour. The rate decreased, keyword there, the rate decreased as time passed and values of the rate at 2-hour time intervals are shown in the table. Find the lower and upper estimates for the total amount of oil that leaked out using N equals 5. So in this case, when we go to calculate delta X, they measured this from the 0 hour and the 10th hour. So when we do our B minus A over N, this would be 10 minus 0 over, over 5, because they want us to use 5 rectangles here. That's going to give us a delta X value of 2. Now here is the difference. When we do our lower estimate, all right, you still factor out the common delta X, which would be 2. But since the numbers are getting smaller as you go to the right, you have to actually use your right endpoints this time to get the lower estimate. So you have to pay attention. Increasing, your lower is your left. Decreasing, your lower is your right. So if I start at 5.3 and I go to the left in 2-hour increments until I get 5 measurements, it will be 5.3, 5.7, 6.2, 6.8, and 7.6. And I'm going to add all of those numbers together. And then I'm going to multiply that decimal by 2. This would end up giving me a lower estimate of 63.2 liters. But since the data was decreasing, our lower estimate actually became our right endpoint. So you have to pay attention to the data that's presented. And then same idea, your upper estimate, you can still factor out the common delta X, which is 2, but since we are decreasing to get the upper estimate, we have to use left endpoints. So I would start at 8.7, and I would do the first 5 measurements in the 2-hour increments. So really you're going to replace that 5.3 with an 8.7. I will write it out for you. So if you were to add all of those decimals up and then multiply that value by 2, you actually get the best number we've had in a while. You get exactly 70 liters. And that would be the upper estimate for how many liters of oil has leaked over the first 10 hours. That ends the video for section 5.1. Like I said a little bit earlier, in the next section, we're going to see some of this stuff again, but we're going to also learn how to work out some of those definitions of area under a curve. See you in the next video.